We are in Algebra 2. Today's lesson is 6-11. Today's date is Tuesday, March 12th, 3/12, 2019. Alright, so, again, this kind of seems like a random lesson to be throwing into our rational unit, but it does have to do with ratios. By the way, another name for variation, when I'm talking about our title up here, and this vocab word variation, is proportion. Everyone write it down. Proportion. If you Google direct proportion and inverse proportion, it'll come up with the same result as direct variation and inverse variation. They're synonyms. So proportion obviously is super related. Is everything okay, Chris? What'd you lose? Oh boy. Well, we will continue on, and someone will get you caught up on the notes. So, it's the back of an ear. Just go grab a Teflon. Okay. Anyway, so coming back, I want to know if things are directly inversely proportional or just directly proportional. I guess I shouldn't say directly inverse because I'm using two words. Anyway, let's move on to comparing them with our table. We're all here. So look at the equation. I can do something like this. I'm going to use m and n. M is equal to kn, where k is some constant. K for constant. Yay. All right, Chris has found the back of his earring. All right, so K stands for some constant. So you can multiply this by anything you want. You can have, yeah, we'll talk about it in a sec. And in the equation over here, you can have something like M is equal to K over N. This is inversely proportional, or inversely variated. I don't know if that's the adjective. Notice that the variable, I'm going to underline the variable here. Gio, can you get the door for us? Please. Our variable is n. N, in our direct variation, is not in the denominator, it is in the numerator. And for inverse variation, the n is in the denominator. This is our variable. That fact alone will probably let you do the homework in about 4 or 5 minutes. It'll go really fast, just with that one rule. Let's see an example. You have to make your own example, and it can't be mine. Here's my example. You have to make your own. Y equals 3x. Ooh, here's one that you probably haven't thought about before. What about t over q is equal to 7? That's also part of this because I can rearrange this formula by multiplying q on both sides and getting t equals 7q. So that's another way of doing it. Inverse variation. What's an example that I can give you? Here's an example. I can say y is equal to 1/3 times 1 over x. I could also do something like, I'll kind of do the same idea. M times n is equal to 10. M times n is equal to 10 is inversely variated because if I divide both sides of the equation by n, I have this form up here, where k again is a constant. So far so good? All right. So there is a symbol for direct variation, and it looks pretty cool. It's kind of like if you look at the symbol for infinity and cut off the right-hand side, that's what it looks like. I haven't ever made it before, and I don't use it very often. Let's see how well I can do it. There it is. I should get... So maybe I should draw infinity and then cut off the right-hand side. But it has this little... That is the symbol for direct variation. It's like infinity with the right side cut off. Sometimes in mathematics, we also use this symbol. It's kind of like approximately equal to, but with just one of them. These both mean the same thing. you won't ever see this on Khan Academy. You'll probably never see it in the rest of your life, but I'm telling you now, I didn't even know this until I started researching this lesson. And I studied math for 4 years in college. Anyway, inverse variation, you're out of luck, bud. You can do a sad face. That's not actually the symbol. If you want to be more accurate, you can cross off the cell. There's no symbol. No symbol for inverse variation. All right, let's talk about what inverse variation and direct variation even mean. So if I'm looking at a table, notice that, and by the way, we're always going to be multiplying today. We're not going to be adding. So don't think about linear things. Think about geometric things. Multiplying. So to get from 1 to 2, what do I multiply by?
2.
Multiply by 2. To get from 2 to 4, I multiply by? Wow, it's the same thing. That's because it's direct variation. So using that fact, how do I get from 1 to 1/3? What do I multiply by? Multiply by 1/3. There it is. So to get from 2 and the y value down here, I'm also going to, shout it out, multiply by 1/3. It's the same on both sides. It's so easy. It's so nice. So 2 times 1/3 is 2/3. Direct variation. It's pretty cool, man. Now take a look over here with inverse variation. Inverse variation, to get from 1 to 2, what do I multiply by?
1, 2.
All right, hopefully we know that we're multiplying by 2. What am I multiplying by to get from 2 to 1/2?
2 half.
2 halves is 1.
No, I don't know.
Oh, did I mess this up?
Pretty sure.
Oh man, Mr. Sindel messed this up.
Oh, my homework today.
Cross off that 2.
Uh-huh.
I totally made that mistake. I'm sorry. It should be a 1. How do we get from 2 to 1? What do I multiply by?
0.5.
0.5, or the fraction
1/2.
times 1/2. What do you notice is happening here?
It's the opposite.
Yeah, it's the reciprocal. Or it's the opposite if you're thinking about the inverse function, the inverse operand. So if you're thinking multiply by 2, divide by 2. But again, try to be thinking of multiplying. So how do I get from 1 to 1/3? What do I multiply by? Multiply by 1/3. So what am I going to multiply by in order to get from 2 to this y value? Multiply by 3, and this answer is 6. That's what it looks like in a table to have inverse variation or an inverse proportional relationship.
What you got?
You see it?
Yeah.
All right. So far, so good?
Yeah.
All right, that brings us to the question that everyone always asks in mathematics.
Well, we should
Yeah, why should we care?
Why should we care? And this lesson is super important in terms of how you apply this to the real world.
Let's just know.
You're in algebra too, right?
We are.
You know, I can show you something really,
You can show me later. Yeah, that sounds good.
like it says that schools should not have algebra 2 anymore. Jay, you probably saw this
What?
in chat. That schools should not have algebra 2
I
anymore.
really want to know more about that, but not right now.
Wait, which chat?
After the lesson.
The Instagram one.
So why should we care? And it's because this is found in nature all around us. Why did we have math? We had math in the old days to make sure that things were nice and easy for us. You're a merchant on a ship and you need to figure out how many sheep to sell, and you want to come up with a variable that just makes it super easy for counting sheep. We have math to make things easy in our real world, although nowadays mathematics is kind of pursued for its own sake, which sometimes happens to be useful for the real world. Do you guys ever know of a situation where math was developed for its own sake because it was fun, but then it just happened to help us in the real world?
No.
No.
My old friend Einstein, he had this
He went
idea.
Thursday.
His birthday is this Thursday.
Is it?
Yeah.
I did not know that. That's cool.
His birthday is Thursday.
It's his birthday is not Pi Day.
It is.
It is?
Yeah.
What? How did I never know that? Oh my God! Mind blown. That means my next child has to be born on Pi Day. All right, got it. I'll go backwards 9 months, etc., etc. All right, so my old friend Einstein, he came up with this idea called the general theory of relativity. Give me a thumbs up if you've heard of that before. General theory of relativity. It's one of Einstein's big things that he came up with. Although it's not the thing that he won the Nobel Prize for, he got that for optics. It's this idea that when you are closer to higher sources of mass, higher sources of gravity, time dilates. I'm going to draw a picture. Don't copy this picture.
Copy it. All right.
So, think about our space, the universe, not as space, but as space-time, as a fabric. Pretend I have a sheet. This is a sheet like a bed sheet. And if I have objects, say this is the sun, say I have maybe plants out here, these objects create distorted fields in this space-time. When I have a heavy object, if I throw a bowling ball onto my bed, that sheet will go down a lot more than if I just throw a pool ball.
Wait, why should we care about what?
About the thing that we're talking about right now, the mathematics, the proportionality.
Wait, you went to numbers to a picture. What do we even do?
I'm talking about this whole other tangent to talk about why math is important, Chris.
Why?
In general, or in this like?
In this case and in general. Right now I'm trying to make it general because you guys were being too specific and I just want to just take a step back and talk about why in general mathematics is cool. When it's studied, okay, this is where I'm at so far on my tangent. We study math sometimes for its own sake because it's fun. Many of you might agree that, well, that doesn't help us if you're doing it for fun. I'm trying to argue now that Einstein did something kind of for fun that didn't apply to the real world, but that does help us in our modern day technology. You use the general theory of relativity every single day by having your phones, by having satellites. Our satellites would be off by like 0.1 seconds every single day without this theory. This idea that time dilates when I have heavier objects on this fabric. So I'm just trying to explain this theory of general relativity, talk about space-time right now. Am I okay taking this tangent, or should we come back to learning math?
Yeah, you're good.
All right. So when I have heavier objects like a bowling ball on my bed versus a pool ball or a marble on my bed, it doesn't distort the space-time as much as other objects. The heavier the object, the more massive the object, the more it distorts space-time. We can all nod our heads, that makes sense. That distortion is gravity. If you think about a heavy pool ball in your bed sheets and you throw a ball that gets really, really close to that pool ball, eventually it'll go and then it will intersect and spiral down into the pool ball because it has this little divot and it will fall into the divot. Can we all visualize that?
Yeah.
I'm just getting a lot of blank stares. Hello, Miss Sassen.
I think you should bring bed sheets in here.
I think we should look up some bed sheets. Do you guys want to see a video to see what this is talking about instead of just imagining it?
Yeah, I'm kind of lost.
Boom.
I was wondering what gravity
explanation for gravity.
It's a 9-minute video. We don't have time for this. Okay, so this, I'm going to silence him so you can't even hear what he's saying. This is an object in space-time. You can think about space-time as some fabric, yeah?
Yeah.
And then when I put a heavier object, that causes space-time to be distorted by the mass of the object. This distortion is what we know as gravity. If things have gravity, it's because things are being pulled towards it. If he throws asteroids out, what's going to happen? They have gravity, so it's going to come and start circling around that object until it either intersects or has a stable orbit around it. By the way, those little marbles still have gravity of their own, but it's almost negligible because they're so small. They're not massive. Our Earth has gravity, but it is almost negligible compared to the gravity of the sun because the sun is so much more massive than the Earth. Let's see what else he does. See if there's anything cool to talk about. Oh, he's going to do 2. Anyway, this is the idea of having space-time. I'm talking about Einstein. He eventually came up with his general theory of relativity. When I am closer to these wells of gravity, time does not behave the same way that time behaves elsewhere, away from that mass. The closer I get to gravity, it elongates time. It makes time longer. That means that if I fall into a black hole that is super, super massive, has so much density, I literally feel like I'm falling through that black hole forever. Time is stretched out so much. This idea of general relativity was just a concept. It was kind of for fun. It didn't really apply to anything. We can't actually go to a black hole. It was all in your head. But why does it help us? Because when you're traveling at such speed, when you're traveling with all this gravity around Earth, it actually does dilate time by such a degree that it will make our satellites imprecise. By having Einstein's theory of relativity, it makes it so our satellites are not off by 0.01 seconds every day, which does add up. That makes it so if I have GPS, I'm accurate within 50 meters instead of 2,500 meters. I can tell where you are within 25 meters versus 2,500 meters because of this fun math that people did that just happened to apply to the real world.
Wait, so where does that ball thing have to do with?
So now that I'm coming back to what this lesson is, I'm talking about direct and inverse variation. One of these rules is, say, has anyone thrown a rock into a lake?
Yes.
I have. Has anyone done it from a cliff?
No.
It's pretty fun. It is dangerous. I could have gone to the real world example of throwing a rock off of a bridge that just happened like a few months ago and killed a person. But let's not do that. By the way, don't ever do that. You will get charged with murder. There are 4 teens that all got charged with murder for throwing a rock off a bridge onto a car that killed a person. It was on their 12th try that they killed someone, so it was obviously...
Were they trying?
They were trying.
Well, it sounds like something else.
But we're not going to be throwing off of a bridge. We're doing off of a cliff into some healthy water down here. Draw your picture. Draw your picture with Mr. Sindel.
Yeah.
Draw a little fish down here.
You can't.
All right, draw a stick figure version of yourself. You are throwing a rock down off of a cliff into some water. Did you know that this is using the same math that we're talking about here, direct and inverse variation? This is direct variation. The speed at which the rock falls, and I'm going to write this down, speed of your rock is directly related, directly proportional, directly, we're not trying to kill the fish unless you're hungry, I guess. Only if you eat it, you can kill the fish. The speed of the rock is directly proportional, so I'm going to do this little symbol. I don't actually know how to draw the symbol very well. Is directly proportional to the square of the time. To time squared. I cannot draw time squared. The speed of the rock is directly proportional to time squared. How many people are going to be taking physics next year?
I don't know.
If you take physics, you will find some equation that looks like this. GT squared
Too much.
or something like this. I don't actually know the equation. You'll notice that you have some constant of gravity. By the way, did you know that gravity is constant generally? I'm speaking very generally. In physics, they always lie to you. Gravity is actually not always constant, depending if you're on Mount Everest or if you're in the Marianas Trench or whatever, Marianas Trench. But assuming gravity is constant, I have some constant number, some negative 9.8 of gravity. This is a constant, and look at this. It's directly related. It follows this form where you have a variable equal to some constant times another variable. In this case, it happened to be the variable squared. This is directly proportional to the square. This is another really important one. This one is called the inverse proportional, or it's inversely proportional. It's called the inverse square law. Write it down. You will hear this maybe once or twice in your life. Okay. Once or twice in your life, and you'll be really smart when you know what they're talking about. This is called the inverse square law. And it's this really cool idea, and it's still in physics. It's a little branch of physics called optics, which is actually where Einstein got his Nobel Prize in. Not for this idea that I'm about to talk to you about, but this is just talking about optics. So if I have some source of light and I'm displaying it really close, then I have a 1-by-1 area that is showing. You can think about this projector. If I have this screen closer to the projector, it will be a lot brighter. But if I move it farther away, it'll get dimmer. How much dimmer, you might ask? The answer is the inverse square law. As I go farther away, if I increase the distance, and I'm about to write down a formula. Are you guys ready? Distance. Distance is going to be equal to, and I'm running out of room here. Maybe I should have written it down here. Wherever you have room. Distance is going to be equal to the inverse Oh shoot, did I mess this up? Brightness is equal to, because we want, the question is how bright is the projector? Brightness. Brightness is equal to the inverse of the distance squared, is equal to 1 over distance squared. That means if I move 1 meter away, then I have to square that and then do 1 divided by that to figure out how bright it is. That means you have this quadratic relationship. I guess it's an inverse quadratic relationship, so it gets brighter much, much faster than a linear line. So if I bring the screen a lot closer, it'll get brighter really, really quick. If I move it away, it'll get dim really, really quick. It's called the inverse square law. It happens with optics. This same square now has to be divided. The same amount of light that would have gone into 1 square now has to go into 4 squares. The same content of light has to now be spread out amongst 4 squares, now spread out amongst 9 squares. So I'm dividing it by the square. Are we all okay with this? This relates to nature.
Yes, sir.
All right, and then back to the boring math.
Even you agree.
Wait, so what the heck was that for then? Do we need to use
I just wanted to show you why it's important.
How is that so stupid?
You don't need to know any of that, but it's fun to know about.
Can I go get some water?
After these, this is like the main content,
I
Gio.
already did it.
What's the answer for number 1? Example 1.
See.
Example 1 is not C. Stay here. Good guess.
Yeah, I say it was D.
It was what?
All right. I need to choose inverse variation.
Wait, why is it D?
Oh.
This A is not inverse. This is actually direct.
Why
Right?
did
Direct
I-
next to it.
Okay, it's D. It's
Oh, what
Wait,
the
I
heck?
use my logic.
This is direct, so it's not A.
It's not.
Wait, how do you know it's direct?
I have some constant, variable equals variable. When you have variable equals variable, you are talking about being direct. Variable equals variable.
So it's D, right?
Oh, wait.
We're going to get there.
Never mind.
If I multiply both sides by n, I get variable equals to variable. This again is direct. It's not B.
Oh, they're all direct.
What about C? What is C?
Direct.
C is neither. It doesn't have to be either one. It's neither.
That's an option?
Neither. It doesn't have to be direct or indirect.
Dude, I told you.
Yeah, he's gonna be like.
And here's your hint. Whenever you're thinking about the graph should generally look like option 1 or option 2. You only have those 2 options. If I have something that looks like this, that's neither. All right, so it's not option C. What about option D?
Yeah, that's
Yeah,
it.
I think
Yeah.
that was Mr. Sindel.
That's what we all-
This is it. This is inverse. It was D.
So you can just guess basically?
No.
Like,
No, I used them.
yo, you guys are being confusing. Okay? Like,
If we can't do anything to this aside from moving around the 4, but I'm always going to have one variable equals to 1 over the other variable times some other constant.
so if there's a number, a fraction with a letter in it, and a number and a letter on the side, it's inverse.
It depends on where the variable is. Is the variable in the numerator or denominator?
It's in the denominator.
If one variable is in the denominator and the other's in the numerator, and you only have multiplication, then it's always going to be inverse. What about E? What is E?
Neither.
It's not neither.
Is it both?
It is not both. It cannot be. It is physically impossible for it to be both. E is,
Directo.
it's direct.
What's like a food?
So it's not E. Let's talk about example 2.
B.
And by the way, let me label these. This one is direct,
I think it's.
Whoa, man.
and yellow is indirect,
I agree.
or inverse.
I think
Yeah.
See?
Yeah, we'll go with B. Yeah, let's go with B.
All right, what is A?
Nothing.
Neither.
Neither.
Nope.
It's
Oh my god.
Inverse.
Divide both sides by M. If I divide by M, I get this, and it's N equals something with,
Inverse.
yes, it is inverse.
God. You know what you want?
Hold on, Gio. Give me 30 seconds. Multiply both sides by N. This one is direct. This one's the answer.
Woo!
Drink water, yeah?
Label all these, and then you can go. This one is called what? C is called
Neither.
Wait, you're allowed to.
Nope.
Direct. Inverse. Inverse.
It's inverse. It's not C. It's inverse because I have a variable in the denominator and one in the numerator. This one is also.
Inverse.
Inverse.
And the other one is neither.
Don't tell me it's
You're good, Gio. And this one is neither.
Wait, I thought it was supposed to be inverse.
No, it's
supposed to be
direct.
Wait, I think this picture is wrong. This is not the inverse. Yellow is
Yeah, I know, right?
whatever. Disregard this picture. That's not correct. Sorry about that. Go ahead and write your summaries.